Hey, this is Ilari from On Humans. I hope that you've had a very good 2024 and you're having a great new year 2025. Something that's now shaping to be a tradition, I thought of sharing as a rerun the most popular episode of the past year. This one was episode 30 with Donald Hoffman, which actually was split originally between two episodes, 30 and 31, and I decided to lump them together. The first hour, which was episode 30, discusses Hoffman's scientific work, and the second half an hour or so, which was episode 31, is more us talking about its relationship with spirituality, religion, and the meaning of life. So here they are in one epic journey towards the frontiers of human understanding. I hope that you enjoy this, and I hope that you have a great new year. So here we go. This is the On Humans podcast with your host, Ilari Mäkelä. Probably the single most famous image in the history of philosophy is that of Plato's cave. It's a bit of an odd image if you make it very clear in your mind, but basically a few people living inside a cave, being chained to stare at the wall. And on the wall they see all sorts of fascinating things happening. But all the things that are happening on the wall are actually just shadows that are created by puppet masters behind them. Now one day, one of these people goes outside of the cave, sees that the real world is made of all these three-dimensional things, the light of the sun, which is what really creates the shadows. Goes back, tells people that what they've used to know as reality is nothing but a projection, a shadow of reality. Of course, this philosopher is ridiculed, and a lot of drama follows. This is the kind of idea that inspired Matrix, the film, where the whole world that people are used to looking at is but a computer simulation run by evil machines to keep humans occupied in their slumber. My guest today is a very serious scientist who believes that something like this is actually happening. No, there are no evil machines. There are no evil puppet masters. There's actually nothing evil in this story. But there's a lot of mathematics. There's a lot of cutting-edge physics. And in that sense, this is a very fascinating story. So my guest is Donald Hoffman, a very notable cognitive scientist, famous mostly for his book, The Case Against Reality. Hoffman's thinking starts from some pretty basic ideas. Perception simplifies the world a lot. A lot of information is lost. Our brains create icons for things. And this sounds all fair and good. I mean, think about color. Is the red flower really red? Perhaps not. It just has a certain kind of surface, reflecting light at certain frequencies. When those frequencies hit our eyes, our brains eventually create the sensation of color red. In a sense, of course, then, redness is inside our head. Most of us are quite happy to do this with colors. But why do we stop there? Why is redness inside our head, but the shape of the flower is really there in the world? The three-dimensional shape, the structure, etc. In a sense, what Hoffman is doing is taking that idea that we feel relatively comfortable with in terms of color and applying it across the board. And that ends up being a pretty mind-bending theory. The redness is inside my mind. Oh, the whole flower is in a sense inside my mind. Oh, my head, my brain, my neurons are inside my mind. But it is a fascinating theory, not only because it leads into some very exciting science, but also because, as we discuss in the second half of this conversation, it addresses directly one of the most fundamental mysteries in modern science and philosophy, the so-called hard problem of consciousness. Now this harks back to episode 17 that I did with Bernardo Kastrup. That was titled, Could Mind Be More Fundamental Than Matter? And that turned out to be the single most popular episode on the show's history. The problem that we discussed with Kastrup is how can it be that our inner life, full of meaning and feeling, could emerge from something feelingless, meaningless, the atoms, the molecules, the neurons, which modern science tends to say that the world is made of. Well, Kastrup says that's the wrong question to ask, because for him, mind, the feelings and the meanings are somehow fundamental. And one way to look at what Hoffman is doing in his work and what our discussion is going to be about is an attempt to flesh that out in terms of what does it really mean? How can we accommodate that with the incredible success of physical sciences? It's a fascinating picture, and it's not necessarily the right picture, but I think it's worth taking an hour and do our best, taking it seriously. To help you do your best, I included a lot of names, links, etc. in the show notes. And as always, do consider supporting the show. Do subscribe to it if you haven't done so. Do give it a nice review if you haven't done so yet. And if you do want to join the lovely group of people who are actually supporting me financially, do head to patreon.com/onhumans. I really, really thank you for you considering it. It makes a huge difference, and without that, I couldn't keep the show alive. Anyway, let's get the show started with Donald Hoffman. Professor Donald Hoffman, welcome to On Humans.
Thank you very much for inviting me. It's a pleasure to be here.
I think for me and for many people, probably the easiest way to understand the way that you came to think about perception is to think about computer interfaces. I've heard you say this, this was kind of for me the moment it clicked, is that there is a trash can icon on my desktop. In a sense, it's very real. I drag my dissertation to the trash can icon and holy moly, it's very real. But on the other hand, there is nothing in the kind of underlying reality of the computer. There is no two-dimensional space where the document is on the left and the trash can is on the right. It's a very, very useful interface, but it is so far from what the reality is actually about. And you're saying that our perception of the world is a bit similar.
That's exactly right. And this is on evolutionary grounds. Evolution by natural selection entails that our sensory systems evolved to guide adaptive behavior, period. And in that sense, very much like your desktop interface. It's there to help you have adaptive behavior toward a very complicated thing, namely the millions of circuits inside your computer. That's an incredibly complicated thing. If you had to toggle voltages to write emails or take photos or whatever, it would never get done. So your interface is there as an adaptive guide to controlling your computer, even though you could be utterly ignorant about what's going on inside the computer.
So basically, there's two creatures that have to write a dissertation using a computer. One of them sees the reality of voltages and the other one sees the interface. The one who sees the interface is going to do a lot better.
They're going to do a lot better. It's so hard to toggle because you have to toggle the voltages, millions of them, in a precise order. If you get it wrong at all, it's wrong. So the interface is actually there to allow you to not only to ignore the reality, but also to successfully control that reality. And that's what evolution by natural selection does. It shapes sensory systems such that they will guide adaptive behavior. But a lot of us intuitively feel that somehow seeing the truth is part of having an adaptive interface. Right? Surely it's more adaptive to see the truth than to not to see the truth. That seems the intuition. And that's where that user interface analogy comes to the rescue. I think with the computer, seeing the truth is not going to help you. Toggling voltages is really, really hard. If you're playing a video game, like a Grand Theft Auto, and you have a nice little VR headset and a little steering wheel and gas pedal, and you can play the game with that, and there's some geek who actually sees the circuits in the software and is toggling and trying to beat you. Well, good luck. So to play the game of life, evolution gave us a VR headset, and that's what space-time is. Space-time is a headset, and all the objects in space-time are objects that we render on the fly, just like in VR. In Grand Theft Auto, I look over to the right and I see a red Ferrari. Well, there's no red Ferrari in the supercomputer. If you looked inside, there's nothing like a Ferrari in the supercomputer. The Ferrari is rendered and perceived by me when I look over there, and as soon as I look somewhere else and see a green Mustang, then the red Ferrari is completely gone. My friend who's playing, if it's a multiplayer game, and I have a friend in Europe who's playing with me, maybe my friend will say, I still see the red Ferrari, but that's because my friend is seeing in her headset and rendering her red Ferrari, which is not the same as my red Ferrari, although they're coordinated by the software inside the computer.
I mean, this is all very, in a sense, this is very dramatic and fascinating. And for the more mathematically oriented one, you have a fair bit of work with this, their simulations. There is a proof suggesting that evolution would work this way. I don't want to get too deep into that because whenever there is a proof, there is a lot of technical assumptions. And I want to still work on the kind of pretty general, talk in the general level here. But at least let's anybody who says, well, that can't possibly be the case, well, it certainly can be the case. But there is a way in which this, I can hear someone being like nodding and yeah, I mean, absolutely. The world is made of quantum fields. I had this lovely moment. Back when I was doing my undergrad, I often had lunch with a friend from the physics department. He was actually a postdoc. Um, but I once was like, come on, you're a physicist. Just tell me what the world is made of. Like, we try this all the time at the philosophy department. We get nowhere. And he was like, oh, it's easy. Excitations in fields. That was his kind of,
Right.
that's, yeah, it's as easy as that. Well, let's take his point of view. I mean, that the world is made of excitations in quantum fields. Yes, there is no table in the kind of strict sense. The world is much weirder, much more difficult. If I were to actually try to interact with the table and the coffee cup, knowing about what's happening with excitations in quantum fields, I would be as miserable with the game of life as someone who's trying to play Grand Theft Auto by looking at the voltages. But that's not actually a very radical claim. I mean, they would say that this is a dramatically simplified interface that we have, and indeed, we only see this very, very small spectrum, even on the electromagnetic spectrum, and so there is all of this kind of. I can hear people being, yeah. Of course, Professor Hoffman is right as far as this goes, but that's not so radical, and you do make a claim that is more radical. So what is the difference between just taking physics seriously in this kind of way and taking the whole package that you're offering?
Right. Well, actually, a subgroup of physicists called the high energy theoretical physicists are actually saying the same thing that I'm saying, which is, and the way they put it is, space-time is doomed. So David Gross, for example, in a 2005 paper says that space-time is doomed, and then quotes several other physicists. And since then, Nima Arkani Hamed, who's at the Institute for Advanced Study at Princeton, is saying quite loudly that space-time is doomed.
If I understand correctly, what they're saying is that the idea that this three-dimensional space plus time, which Einstein fused into a four-dimensional space-time, is almost certainly not the most fundamental reality.
Exactly right.
But there are people who say, yeah, okay, well, we get string theory, where you have, I don't know how many dimensions you have. But
Right.
how close is it just to like go? Let's go a little bit deeper. We get some vibrating strings in more dimensions rather than this three dimension. Is that's not what you're saying? I know that's not what you're saying. So I'm just trying to get to the real, the real distinction.
Yeah, that space-time itself is just the wrong concept. And quantum fields inside space-time are actually a fairly crude hack computationally. And then this is coming out of the new. So what Nima and colleagues are finding are new structures utterly outside of space-time. So they're not like hidden dimensions curled up inside space-time, like we tend to think about the extra dimensions in string theory as curled up inside space-time, but they're so small we can't see them.
I see.
Whereas when you say space-time is doomed, and you're getting new structures outside of space-time, these are not like curled up inside. No, space-time itself is utterly kaput, gone. There's something entirely outside of space-time, and space-time ends up being a trivial projection of these more fundamental things that are not curled up inside space-time. They're utterly outside of space-time. Things
By the way, at least in the beginning, I want to kind of keep this as much as possible on the level of possibility that rather than certainty. So just exploring kind of how well this view, how possible it is rather than how certainly true it is. But I do want to ask here, how many percentage of high energy physicists do you think would agree with the strong space-time is doomed claim versus a kind of, well, yeah, it's definitely, we need a little bit more funky dimensions or something, but we can still broadly come out of it with something recognizably similar to what we think at the moment of space-time?
I don't know what percentage, but I would say that David Gross has said this, who won the Nobel Prize for his work on quantum chromodynamics. Ed Witten has said this, who's one of the fathers of M theory, or the father of M theory. Nathan Seiberg, who's at the Institute for Advanced Study, Andrew Strominger, and Nimar Khani Hamed.
So a
Graduate
serious
students.
list.
It's a pretty, I mean, these are professors at Harvard and Princeton.
Yeah.
And David Gross is at, I think, UC Santa Barbara.
And
But
for listeners, I don't worry, there will be, as always, a list of all the scholars we mentioned in the show notes. So if you didn't catch all of that in one go, don't worry.
right. So the percentage, but put it this way, in 1905, there was one guy that was saying that space and time were doomed, and that we had to have space time, and that was Einstein. And it didn't matter that he was just the only one.
Yeah, fair enough.
Right.
Yeah.
But here we have a whole chorus of brilliant physicists, and what they're able to do, by the way, is it's not just space time is doomed, but they found new structures beyond space time that let them predict so-called scattering processes. Like 2 gluons colliding and 4 gluons spraying out, or something like that. And they can actually compute those scattering amplitudes with the new mathematics that they're finding outside of space-time. If you do that using quantum field theory and standard quantum computations in quantum field theory, it's hundreds of pages of algebra. It's an incredible mess. You do that with the new structures that they found outside of space-time, it's 3 terms you can compute by hand.
This is like the amplituhedron.
Yeah, and what Nima and colleagues do is they actually show you formulas that they can compute outside of space-time that give you the right answers, and the answers are very, very simple: 3 terms, 4 terms, 5 terms, instead of millions of terms and hundreds of pages. So what we're realizing is, when you're working in space-time and quantum field theory, it's such the wrong framework. You've lost so much information that the mathematics becomes unnecessarily hard and complicated. So this is a hint that we're onto something. What these structures are about is a big mystery. So the amplituhedron and these decorated permutations, which are behind the amplituhedron. Decorated permutations are permutations, like shuffling cards, right? What's being permuted outside of space-time? What's going on out there? No one knows. It's
even saying out there is so confusing, because of course when we say there, all we can imagine is a space there.
No, I agree. So maybe a little help on that point is, if you think about space-time as just your VR headset, and when I say what's there outside of space-time, it's sort of like, so space-time is just a VR headset that I'm wearing, and the question is, what is outside that VR headset? That's how I think about it.
I mean, the Matrix fans will get very, very excited.
Love that.
Yeah. Okay, so when my question was, well, isn't all you're saying kind of just like what anyone who pauses to think about the fact that the world is made of some pretty funky physicist stuff and IC tables and chairs? What you're saying is that it's not the same as the standard version of that, but yeah, actually it is just the same version as the more kind of cutting edge, what physicists are saying, version of that, which is that.
It's saying that space and time themselves are not reality. They're not fundamental reality, and so therefore nothing inside space and time. No quantum fields inside space and time are the fundamental reality. No particles in the so the bosons, leptons, and quarks are the standard model of physics, which are excitations of the quantum fields of space-time. All of that is an artifact of the headset that we're wearing. There's not the deep reality. And so, to be very explicit, no particle, no photon, no electron, no quark has any definite value of position, momentum, or spin when it's not observed. None. That's well established.
And that's that is the mind-bending thing about quantum mechanics that I think makes people, even like myself, who really doesn't understand the mathematics, come back to it again and again and again, to any popularization of it, trying to be like, what is going on?
That's right.
There's another actually thing that I think less people might be aware of, which resonates so strongly with this idea of the interface, the computer interface or the VR interface, which is something that I have to admit. I mean, I've spent a fair amount of time with popular physics, and I just cannot do the math, But I've done. During COVID, I was in New Zealand. I was going my then girlfriend is New Zealander, and so we spent a fair amount of time, of 9 months, 8 months in New Zealand during the lockdown periods, which was wonderful. But when we went there, we were in a quarantine hotel for 2 weeks. It's one of the best 2 weeks of my life, honestly. It was just so wonderful. Just my desk, just time to spend together, and with studying whatever I wanted. Nobody can even reach me because I'm on the other side of the world, so they're asleep when I'm up. It was a funny experience. But anyway, back to the point. I took a quantum mechanics course, which was this kind of, I can put it in the show notes for people who are interested. It was a really well designed quantum mechanics course on Coursera, which kind of tried to go through the mathematics with very simple mathematics. So it was kind of for people like me who know who can kind of follow super simple math. So it wasn't just words, but it was not complicated math, and it was really useful. And I watched a lot of Sean Carroll's Biggest Ideas in the Universe videos, which is a similar idea. Like, he does use math, but the most simple math possible, to kind of try to find the middle ground between pure words and math that loses 99% of the world population, maybe.
Sure.
And so I'm not coming at this from like, I didn't know anything, of what's going on. I've really tried, but it's so difficult to penetrate this without the math. But I didn't know that there is a thing called the Planck length and Planck time, which is an incredibly small kind of nugget or space-time. And below that, space-time doesn't make sense.
That's right.
That sounds like a pixel. That resonates so strongly with the idea of you zoom into the computer screen further and further and further and further. And at some point, you're like, wait, it doesn't make sense anymore. This is just, it doesn't, what's going on? And that is very textbook stuff. So can you talk a little bit about that idea of there being this pixel size that we know of space-time?
Yeah, now that's a point that David Gross made in his 2005 paper when he was saying that space-time is doomed. He was saying that it has no operational meaning beyond the Planck scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds. And that might seem pretty small to most people.
I mean, it's very small.
From my point of view, it's, space-time falls apart at 10 to the minus 33 centimeters, not 10 to the minus 33 trillion centimeters, just 10 to the minus 33. It's a cheap headset. We got a real headset. And only 10 to the minus 43 seconds, not 10 to the minus 43 trillion seconds, just 10 to the minus 43. So,
okay, fair enough. Yeah.
3 dimensions of space, 1 dimension of time. Seems like we got the low quality, cheap model. So space-time, in some sense, we're maybe over-impressed with space-time. I think I'm completely underwhelmed with it. I can imagine, from the point of view of evolution, by natural selection, right, for evolving headsets that are much more interesting. There's no principle why we couldn't imagine, have a 4-dimensional space, right? Right now, I can imagine a 3-dimensional cube, but if I try to imagine a 4-dimensional sphere or a 4-dimensional cube, nothing happens, right? Well, I felt cheated. I want a refund. I want a better model. I want a better headset. So
that's really funny. I want to get back to the physics towards the end, because you have some really kind of mind-bending suggestions on how to rethink physics from the deep end of the pool that we are still kind of on the shallow end of in this discussion. So let's get to that, but bracket physics for a while and maybe think a little bit more about just conceptually. I mean, a couple of clarifications. One thing is that one of the ideas that people, I think, are quite familiar with, one of my really good friends back also during my undergrad, not this time, not a physicist, this time a mathematician, gave me once a book. I think it was by, is it James Abbott or David Abbott, I can't quite remember now, called Flatland.
Flatland, right?
Do you happen to remember the name of the author?
It's Abbott, but I forget the.
Yeah, anyway, the story of a two-dimensional space where objects move, they're rectangles and triangles and whatever. And they couldn't believe the idea that there's a three-dimensional space out there. And it's really well told. If I get it right, you're actually saying something a little bit more radical than the idea that there's kind of an extra dimension from where we are projections. So you're really saying that it goes even deeper than that, right?
That's exactly right. And that's what, by the way, it's not just me, it's the high energy theoretical physicists like Nima and others who are saying that we're looking for structures entirely outside of space-time.
Yeah,
And
not just a
entirely
bit more
outside of time.
complicated space. Yeah.
Right. It's not just extra dimensions of space and time and so forth. It's entire. And by the way, it's not just letting go of space time, but also letting go of quantum theory and quantum field theory.
Not letting go of it, but seeing it as a special case of a more fundamental theory, right?
That's right. Letting go of it as the fundamental, as being fundamental, and seeing it as derivative, as a projection of something far deeper. So space-time and quantum theory will emerge together from a far deeper mathematical framework.
Yeah, it is fascinating. I mean, I think I've been a Kantian, I think, for 12 years about reality. And it wasn't because I read Kant. I think there are many 18-year-olds who are smarter than me and who can actually read and understand Kant. But for me, it was the high school textbook version of Kant. And I kind of realized it afterwards. I remember when I turned 18, it was my 18th birthday. And I was really into philosophy. I was going to apply to study theoretical philosophy at the University of Helsinki that spring. And I had I remember this sudden realization where it wasn't a realization, because of course I might have been dead wrong. I might still be dead wrong. But I had this, it was inspired by something completely almost nonsensical in this context. I was at the Helsinki Design Museum with my parents. And there was this very famous quote, "Form follows function," just written on the wall. And I remember somehow my 18-year-old brain looking at that quote and thinking about the idea that if there would be no mentality, nothing kind of trying to find function in the world, I just don't know if there would be forms. I don't know if this thing that we look as three-dimensional forms would exist without there being this kind of mind constructing it somehow. And when I later learned about Kant, I was like, oh yeah, that's kind of exactly what I thought. And it was very unstructured, creative young brain, just concocting ideas in a way that I didn't really have any argument for it. I was just like, yeah, I think that's how it goes. But Kant has been quite kind of special to me in that way. It sounds quite similar to what you're saying, because Kant says that there is the Dinge an sich, there is the reality as it is. We can't know about it. What we have is these structures like space, time, causality, these things that we kind of concoct the reality to fit into those categories. Our mind does it. And that's kind of all we can ever know. For those who are not so deep in physics, but might have a more philosophical background and have read Kant, how much is this a kind of mathematical 21st century Immanuel Kant rephrase versus how much is it is it actually a superficial similarity and you're saying something very different?
Well, it's similar. He has the distinction between the noumena and the phenomena.
Yeah.
And
the noumena being the things as such.
That's right. And the phenomena being our perceived world.
Yeah.
And so I'm making a similar kind of distinction. He said that we could say nothing intelligible about what was beyond the phenomena. And physicists are bravely going out there and writing down mathematical models.
Yes, I see. Yeah.
So and I'm also doing that. So I disagree with Kant might be right. Maybe we will find that we can't do it, but we're going to go down trying. So one thing we're empirically disagree. I mean, in terms of what we're doing, we don't say that you can't start to talk about the noumena. we're trying to build mathematical models of it and scientific models of what's outside of outside the phenomena of space-time. So at the top philosophical level, yeah, I'm in broad agreement, but where we disagree is, of course, pretty critical.
Yeah.
And if I really said there's nothing I could do about the noumena, I wouldn't be doing any of the research I'm doing.
Yeah. I
So,
mean,
so there
Kant's
I
conclusion was that therefore we continue doing science about the phenomena and zero problem. We also have faith in God, in the noumena. And this is a beautiful solution for him because he doesn't need to be bothered about science anymore. And nobody can prove God, which he detested the idea of, because then there is no faith.
well,
um,
and Kant might be right, and I might be wrong.
uh,
Who knows? I'm just saying that
yeah.
for better or for worse, we're trying to at least take some. Now, what might be the case is that we can take a few steps out of the headset, out of the space-time headset. But maybe Kant is in some sense ultimately right in that we would never, and on this point, I would agree with him. We never are going to have a theory of everything. It's the very nature of scientific theories that they make assumptions,
Hmm.
and those are the miracles of that scientific theory. Are its assumptions, and there's no scientific theory that doesn't start with assumptions. So in that sense, yeah, Kant is absolutely right. We'll never have a theory of everything. And by the way, it's good because that gives infinite job security to science.
Yeah.
Right. It means there's the next generation will always have the task of
Yeah, yeah,
bettering the theories that they receive from their seniors.
yeah, yeah.
So we'll always be working towards better theory, but we certainly can have theories that go beyond our current phenomena. So there I disagree with him. So we can go beyond our current phenomena. Ultimately, we're going to have to test our theories in the only place we can test them, which is experiments in our phenomenal realm where we can actually experience them. But we can have theories of structures beyond our phenomena. But I would probably agree with Kant then that in some ultimate sense, we can never get the theory of the noumena fully. There is a deep fundamental mystery at the heart of everything.
Okay, well, now that we are in the kind of business of contrasting your view with first ring theory and Kant, and maybe we should quickly just highlight that some people might get a kind of aha. This sounds a little bit like the simulation argument that we might be living inside a computer simulation. But you're saying something actually really different, right, from the kind of classic simulation argument by Nick Bostrom, because what he believes is that there is a base material space-time reality, that's the real deal. But we only live inside a program, which is kind of less real than that base bulky reality with desks and computers. But you're saying kind of something is almost the other way around. It's like any reality where you really have desks and laptops on it is part of the non-base reality.
Exactly right. So
Okay.
yeah, Bostrom and similar versions of the simulation theory say that what we're experiencing right now is just a simulation from some smart hacker on their little laptop somewhere. But
Yeah.
that hacker and their laptop are part of a simulation at an even deeper level. And at that base level, though, they think of it in terms of a physicalist space-time. And some real space-time hacker
Yeah.
in three dimensions of space and one dimension of time or whatever, so string theory world, whatever it might be. So I'm saying, no, you're not thinking outside of the box enough.
Yeah.
Any
Yeah.
space-time for the base is that you're still in a VR headset. That's
Hmm.
but they make another difference, another claim that's different from what I'm claiming. They're saying that my conscious experiences right now, my headache, my taste of chocolate, all of those conscious experiences are due to a program. Somehow a program is creating those conscious experiences. And there's not a shred of theory that supports this in the following sense. There is no theory that any of my colleagues, and I good friends with many colleagues who are working on physicalist theories of conscious experiences, so integrated information theory, global workspace theory, work straight collapse of quantum microtubule states, and so forth, attentional schema theory. They're all the brilliant colleagues and friends who are working on these theories, trying to show how physical systems with the right kinds of computational structures or whatever functional structures can somehow give rise to conscious experiences. And here's the state of play. Pick any specific conscious experience that you want. Taste of chocolate, smell of garlic, sound of a trumpet, and ask any of these theorists, can your theory give me any, what specific conscious experience
Yeah.
can you account for? And the answer is none.
It
There
is
is
actually
no theory.
striking when you put it that way, because that's the hard problem of consciousness is so often couched in a kind of generalized language, like how could any state be conscious?
Right,
To which it's so easy to say, well, give us some time, like we'll figure it out. But
right,
when
right.
you put it like we've had a few decades of really hard attempts, and there is not a single theory which is even close to explaining a single individual conscious experience. And I guess just to make it clear, do I understand it right? What you mean is that, let's say, the classic example from neuroscience, the V4 cortex and color vision. We simulate the V4 cortex, we experience color. Why is it necessary, based on my theory, that when it's the left bit of the V4, it's blue, and when it's the right, it's red? And it has to be. It could never have been the other way around. And that would be an actually physicalist theory of color experience, and that there is not a single instance of anything like this being even suggested to be anywhere in the near distance. And when you put it like that, it is actually a striking failure. I don't know if you formulated it, or did you learn that formulation from others? Because I have heard very senior people like Philip Goff, very, very senior philosopher of mind, say that he has borrowed that argument from you.
I don't
Did
remember
you get it
reading
from
it
someone?
anywhere, so I just don't remember someone making that specific claim.
Yeah, because it is a very precise and scientific claim, in a sense that's we don't want to hand away the explanation of, whenever you have integrated information. Yeah, and by the way, I love integrated information theory. I think that there are aspects of it are just fascinating and really revealing. But yeah, I mean, why is that bit of integrated information? Why does it have to be the taste of vanilla? And why can it absolutely not be the taste of chocolate? There isn't anything even remotely close.
There's nothing. I actually asked Giulio Tononi this question. He came and visited the Helmholtz Club in the late 1990s at UC Irvine.
Yeah.
So he presented his theory then, and I asked him this question then, because it seemed to me the natural hard-nosed question to ask. And he had no examples. And I asked him a few years ago at a physics conference, and he said again he didn't have one. They've since published a paper on their theory for space. So they have one paper where they're trying to say this is the IIT Q shape for space, and I'm in no way convinced.
But it is
So
an interesting development. Is that paper out already, did you say, or is it
there's a
coming?
paper. There's a paper out, and
Okay.
I find it completely uncompelling. There's nothing on it that's compelling. But at least at least they're trying. And I should also say that the philosophers, for example, like Keith Frankish, who's a friend and a brilliant guy, or Dan Dennett, who say that conscious experiences are illusions. So they're physicalists, and they're saying conscious experiences like the headache or taste of chocolate, these are all illusions. You might say, okay, well, that's a good move because now that they're free of this problem that I'm putting
Yeah.
on. But no, they're not, because they have to explain what is the pattern of brain activity that must be the illusion of the
Yeah.
taste of chocolate and could
Yeah.
not be the illusion of green.
Yeah.
And so they have every bit of responsibility for a scientific theory ultimately, as the ones who say that conscious experiences are real. If you say it's an illusion, well, I have this illusion and not that illusion. As a scientist, I'm hard nosed. Give me a specific theory why this pattern of brain activity or integrated information must be the illusion of the taste of chocolate and could not
Yeah.
be the
Yeah.
illusion
Yeah.
of the.
Yeah.
So I mean, I'm interested in science. I'm not interested in hand waves. I have no interest at all in hand waves or one-upmanship. I want theories that work. And what's interesting is that my colleagues who are physicalists have chosen a research program for themselves in which they say, I assume that space and time and physical objects inside space and time and their functional properties are fundamental. And so they're fundamental. And if I also believe that conscious experiences exist, but are derivative from these, then I have to explain how these physical functional properties of physical systems give rise to the taste of chocolate, the smell of. So they have set themselves up that problem. Now, They don't have to choose that problem, but they've chosen to have that problem.
Yeah.
As Steve Pinker, when he likes the global workspace theory, and Pinker in his book Enlightenment Now in 2018 says he likes it, but he points out that it can't explain specific conscious experiences, and he says the connection may have to be stipulated. So the connection between this physical system, like some global workspace architecture or whatever it might be, or integrated information, and this specific conscious experience may be something that we have to just stipulate. So it's not really an explanation; it's a stipulation.
Yeah.
So I agree with Pinker. I
And
think
it's not one stipulation. It's not like, well, we just stipulate that there is something that it is. Because I used to think about probabilities. We just have to stipulate that there is something that it feels like to be a physical process. Okay, done. One stipulation. But you're very, very right. No, you have to do every single time. And we just stipulate that this feels like the taste of vanilla, and this.
There are millions of stipulations. Millions.
Yeah. It's not as easy as just one here.
We have a choice between physicalism, either the ones that say consciousness is real, or ones that say consciousness is an illusion. In either case, they're saying we're going to start with we assume space and time, we assume the standard model of physics, whatever it might be, we assume that. And we're going to also end up having to stipulate the conscious experiences or stipulate the connections with the illusions of. So we're going to stipulate those conscious experiences or the illusions. And I come back and I say, well, how about this? I will only stipulate the conscious experiences, and I will show how space and time arise from that. So I will stipulate less than you. I will only stipulate the conscious experiences outside of space-time and show that space-time arises as a headset inside this deeper theory. So let's take our theory of space-time itself, Einstein's theory and quantum theory, and ask ourselves, what do they tell us about space-time and the reality of space-time? And what they tell us is that space-time has no operational meaning past the Planck scale, right? They tell us that space-time is doomed.
Well, they don't exactly say space-time is doomed. I mean, I'm sure that there are people who are aware of the way that Planck scale work and says either adopt something like this, like string theory, or adopt something like, I mean, I don't know, for example, with like, just to get too technical, but like Roger Penrose's like twistor theory. I don't know how different it is from the way you approach it, but I mean, there's just so many theories in physics that I don't know, but I think it would be misleading to suggest that just the appreciation of Planck scale being this kind of pixel, I mean, it resonates with your theory, but I don't think it necessarily leads into it as the only possible outcome.
Well, most physicists don't think this space-time is doomed. Most don't even realize that there are these physicists, high-energy theoretical physicists, who say that. I was at a conference a little over a year ago where a number of quantum theorists, professional quantum theorists, were talking about their theories of consciousness. And at the end of each one, I asked them, what do you think about the research in high-energy theoretical physics that says that space-time is doomed? And to a person, they hadn't heard of it. And these are professional physicists. So this is a small group, but it's the group of theoretical physicists who are pushing the high energy limits of our current theories. They're the ones where the Planck scale matters, right?
Okay,
that's on the horizon. Yeah. So for everyday, condensed matter physics and so forth, you don't have to worry about, space-time is doomed. You can continue if you're doing molecular, quantum molecular biology, whatever it might be. That's perfectly fine. It's only when you're at the theoretical edge of modern physics, you're saying what's beyond the standard model. It's the physicist you would expect to be facing.
Okay, yeah. Well, can I ask you something? I mean, I really want to continue on the hard problem of consciousness. I think that's the reason this fascinates me so much, is the way you approach it. But I think in the kind of science philosophy podcast world, the in-house theoretical physicist is Sean Carroll, well earned by his amazing amount of internet presence, making these ideas somehow relatable to folks like me without a physics degree or even a proper grasp of the complicated mathematics. What would Sean Carroll say? Do you know what he would say?
I just interacted with him last Saturday.
Okay. Okay.
We both a conference in New York. So I spoke and Sean and I had some exchanges. So I think Sean is into the multiverse. And he's also thinks that decoherence can take care of the measurement problem in quantum theory. And my idea of, conscious agents outside of space-time, he was not terribly excited about that at all.
Yeah.
He thought that there was the notion of emergent space-time. He said no big deal. Space-time is emergent.
Yeah, so he would say space-time is doomed if as a fundamental fabric of reality, but he just takes a very different turn after that. Is that right?
That's right. And he thinks that multiverse will ultimately be the deeper theory outside of space-time in some sense.
Yeah. I guess the reason I wanted to just get that out there is that I know that it is possible to be very convinced by your argument while not overselling it by saying that it is the only possible outcome of the theoretical physics. And I guess that Sean Carroll would be an example of someone who probably has taken relatively seriously the problems that you talk about. He would take a different turn, and therefore he will have a very, very difficult time with the hard problem, as you have defined it, described it.
Right.
And so that might be a reason to then take your turn. But I guess I just feel like a lot in the physics maybe resonates with this package that you're offering. It makes it very possible, but not necessarily determined like this is the only way we can go. I guess just to make the distinction was the reason. Sure. I wanted to press the point. Would you agree, or am I kind of selling the
Right.
argument short?
I would completely agree with you, and I would say that at the best, if I'm really lucky, I'm taking a good next baby step. At the best. Most likely, I'm just flat wrong. But at the best, and that's the way science is that we're always taking the next baby step. Now, with Sean Carroll, I mean, I don't think that decoherence solves the measurement problem. That might be too technical for this conversation.
Yeah, it might be. Honestly, it might be. Yeah. But maybe if we can keep to the hard problem of consciousness.
Sure.
I mean, what you're suggesting is that we have this really serious problem, which is that nothing in what's happened in consciousness science suggests that we are even remotely close or have made any progress in solving the actual hard problem of consciousness. We get into this kind of generalist, oh, well, this kind of system is conscious, but why does this feel like red and not like green? I mean, the simplest question you could ever ask. We don't even have a way to start. And therefore you make a philosophical claim, okay, well, let's not try that. You have this whole story that we've already talked about why we shouldn't anyway try that, because neurons are objects or processes in space-time, and therefore not fundamental if they are part of the headset, part of the interface, not part of fundamental reality. But then you say, okay, well, what is part of fundamental reality? Are those experiences? And what you do is so difficult. Then the next step is so difficult, I think, for many people to understand, because you have a mathematical theory of how this works. And the idea that there is a mathematical theory, and I mean, I think immediately if we start talking about Markovian dynamics, we will lose everyone. So, I mean, not everyone, but me and a lot of the listeners. So without using the technical terminology of Markovian kernels and whatnot, can you just talk a little bit about how can we even start understanding what it means that you have a mathematical theory of how elementary conscious experiences combine to create a system which, as its projection, has space-time, and which also is so specific that you say that you can run simulations and predict fundamental physics, scattering amplitudes. But that to me, it sounds like this, I don't even know where to start.
Right. So first, just at top level without the mathematics, the way to think about the framework of what we're doing with consciousness is think about the Twitterverse, right? In the Twitterverse, there are millions of Twitter users, and someone tweets and they have followers that receive the tweets, and then maybe forward, they might like the tweet and they might send it to somebody else. So there are millions of users and billions of tweets. If you wanted to really understand the Twitterverse, you could never read all the tweets or interact with all the users. It's just overwhelming, right? So,
Mhm.
so it's this vast social network, and that's what I'm proposing. Reality is the vast social network of interacting what we call conscious agents. But when you have a social network, there is a dynamics. You can talk about social network dynamics. How do pockets arise in which all these people have the same ideas, and over here these people have these? You get these stable configurations of ideas that propagate, and so you get propagations of patterns. And this image goes viral, everybody sees it. This image only goes to this. So you can start to look at propagation through social networks, and it turns out that there's a very advanced mathematics of this, and the companies that are behind Twitter and Google and so forth are very, very sophisticated about the mathematics of social networks. And we're using that mathematics. We're saying, let's have these conscious agents, this social network, not inside space-time. We don't need it inside space-time. The mathematics does not require that they be embedded in space-time. They can just be an abstract network.
A
Now,
platonic network of of some element. Yeah.
of agents that are exchanging experiences. Think about it probabilistically. If Hoffman gets this tweet, what's the probability that this kind of tweet he'll send off to his followers? What's the probability that he won't send the tweet off? So we published a proposal, and it actually won a little award from the Institute of Noetic Sciences back in June, where we're proposing to start with this theory of conscious agents and actually predict from our theory and match what high energy particle physicists have found when they look inside the structure of the proton. At the coarsest scale inside the proton, you see 3 quarks, 2 up quarks and a down quark. When you look a little bit higher spatial and temporal resolution, you see a quark C, quark antiquark pairs that are pairing in gluon C. And when at the highest resolution of space and time that they've gotten, it's just a gluon C. These are the sort of the force carriers of the strong force. It's so, and what they get is momentum distributions. They can tell you, okay, at each resolution, how much of the momentum distribution is due to the 3 quarks? How much is it due to the C quarks? How much is due to the sea the ocean of gluons? We're proposing to actually project our theory of conscious agent dynamics into space-time in such a way that we can actually get those exact momentum distributions to several decimal places.
But that sounds to me like a miracle if you can do it.
Here's how we've tried to pull off the miracle. We have to figure out the projection. So how do you project from a theory of conscious agents into space-time? And here the physicists gave us a big clue. The deepest structure, just in the last 10 years, they discovered the deepest structure they found outside of space-time are decorated permutations.
And by the way, if as a listener you don't know what that means, don't worry. Let's just keep listening. I don't know exactly what a decorated permutation is, but
It's a fancy way of talking about card shuffles, right? And why that's the deepest thing they found. Even the physicists are mystified, right? They're going, who ordered that? Who ordered decorated permutations as the deepest structure we found so far?
Okay, but go ahead. So given that card shuffle thing
is the deepest thing they found.
Is the deepest thing that we have quote unquote found, or a model that could explain the deepest things in a mathematically clean way. Given that, what's the next step?
So what the physicists do is they can take you from those decorated permutations into space-time and actually give you the exact scattering amplitudes for many processes.
Okay.
So we realized if we can connect to their decorated permutations, they do all the hard work of taking it into space-time. They've done that hard work. So what we asked ourselves a little over a year and a half ago, can we take our Markovian dynamics of conscious agents and project it into decorated permutations? If we can do that, then we'll go all the way into space-time because the physicists have done the rest. So we just asked, so have the mathematicians shown how to project Markov dynamics into decorated permutations? We did a search and they hadn't done it. So we did it. We figured out 2 different mathematical mappings. So it's 2 contributions to mathematics. So it was nice. We were forced to do some original mathematics and we projected our Markovian dynamics into decorated permutations. And then the physicists take us all the way into space-time and particle scattering. Now that we had that, we could then ask, what part of our Markovian dynamics of conscious agents corresponds to particles. We know what part of the decorated permutations map into particles. So we could then say, these are the units of our theory that correspond to particles. So we did that. They're called
Okay.
recurrent communicating classes. So the physicists helped us out. They pointed us, we discovered it's these recurrent communicating classes. So then we said, okay, then what corresponds to mass? And it turns out we could figure it's the entropy rate. What corresponds to momentum? It's the number of states in the recurrent communicating class. What corresponds?
Can I ask how surprised were you when you found this? Because given that I just cannot follow the mathematics, let's say that I mentioned before we started that I lived in China and had my time learning Chinese characters there. Now, let's say that somebody who, someone from Europe comes and starts studying Chinese, and they try to uncode the language, and then they find that there is a way to use Romanic alphabet,
Right.
to fully capture every sound in Chinese language, which there is, which is the Hanyu pinyin. If I come and say, look, I can use the Roman alphabet to capture the whole of Chinese language. So actually, the Chinese language is a projection of the deeper linguistic reality, which is that the Romanic alphabet is like this fundamental power. I'm getting kind of off tracks there, because it's so not surprising. It's kind of almost trivially true that I can just map them onto sounds. I create the mapping, and so from a kind of, this is actually quite a trivial finding, the kind of Chinese using Roman alphabet, to, oh my God, this is actually incredible how surprising it is that there was this mapping. Where are we operating? Because I can judge.
We were stunned to discover that all the basic properties that we need to describe a physical particle were there in the recurrent communicating class. And it was so stunning. At this point, we were partway through this, and a particle physicist named Chopin Chandopattier, who's an experimental particle physicist. He's a professor at UC Berkeley, but he works at CERN and Fermilab and he has for about 35 years, something like that, doing designing and building real particle experiments. When he saw what we were doing, he joined our team. And together, we put together this paper that won this little award from the Institute of Noetic Sciences. And to me, it's been a complete stunning experience that this was even possible.
Can you help me understand this reality then? This I don't know if it's a Platonic reality, how should we call it? But this hidden reality of conscious agents, conscious experiences. I mean, what is there? Because you can have the mathematics. I mean, I think the common way to say is that, okay, you can have the mathematics, that what breathes fire into the equations, and you say that what breathes fire into the equations is somehow conscious experience. That's what is there. But I guess what I'm struggling with is that, let's say I'm looking at a new Apple product and it tingles my senses. It just sounds so incredibly human in a kind of trivializing sense, like this is not a very profound thing. Given that the structure of the universe probably doesn't have one element in the same way as we used to think that it has up quarks and down quarks, it probably doesn't have like desire for Apple products and desire for Samsung products deep down there. But what is there that can make up this very uniquely human experience?
Well, it's a great question. So the mathematics that we have starts off with these little conscious agents that have only one experience, say, red, and we look at their interactions. We start to build up more complicated conscious, as big as we want. And we do that because that's what's feasible to do with, technical tools and mathematics. But that mathematics itself our mathematics tells us that approach is limited, because interacting conscious agents form new agents. And that means that we can have, if we start off with a countable infinity of conscious agents, we can get a higher level infinity of their combinations. We can take a bunch of them, have them interact, that combination is a new conscious agent. You get new levels of infinities. And so what we realize is our theory is telling us there's ultimately one big conscious agent, maybe. There's one. But you'd have to climb up all of Cantor's hierarchy and beyond to get to it. So we can't. But our theory points to it and says you'll never get there. So right. So but that's what a good scientific theory does, right? A good scientific theory tells you its limits. So Einstein's theory of gravity says space-time is a wonderful structure until you get to the Planck scale, and that's the limit. Then it's gone. So a good scientific theory tells you the scope of the theory and the limits of the theory. And our limit is, our theory says looks like there's one agent, and everything is a projection of that one agent, and you will never model that one agent. But you can model these projections and projections of projections. That's what you can do, and you can make testable stuff there, but you'll never get to the one. So that's where I am right now. Now, the question is, what can we say about the one?
Well, Kant would want you to say absolutely nothing except that we have more maybe reason for faith.
and Kant might be right.
But please, I guess the reason I said that, I mean, half a joke, but half to just point out that is a there's a deep spiritual potential.
Yes.
And if the term God comes to someone's mind, I don't think it's completely, ordinary.
Right. And I think that, I have a lot of interaction now with people from spiritual traditions because this part of the theory really sort of resonates with things they've been saying for thousands of years. And for what it's worth, my own guess right now is that you and I are the one, just using an avatar. So it's the one talking to itself through billions of human avatars and cat avatars and mouse avatars and tree and plant avatars. These are all just interfaces that the one is using to explore its potential. And I can't know the one in a conceptual sense, but I can know it directly because I am it. But now I've gone on that part. I've gone beyond my science. Where the science goes is all the finite collections of conscious agents and their properties and mapping into space-time. That's the science. This other part is me reading the tea leaves of the math and saying, this is, Hoffman's best guess. And maybe it's also informed by what I've read in spiritual traditions, and maybe don't take it too seriously, but so I'm just putting out where I'm thinking about on that right now.
Are you religious?
Well, I'm not practicing any particular, I don't attend or anything like that, but I meditate daily.
Can I ask what kind of tradition?
It's the meditation is just going into pure silence. It's close to but some versions of Buddhist meditation techniques. They're very, very similar, of just silence and then returning to silence whenever thoughts or distractions occur. But I do it without any particular posture or no mantra or anything like that. It's just going back to silence. So I don't think, I wouldn't say I'm any devotee of any particular religion. My dad was a Protestant fundamentalist Christian minister for a while. So I was raised in that, and I've read the Bible cover to cover more than once. So I know the Bible quite well, and I think that there are beautiful things in there, and there are also things that I disagree with. And my guess is that science and spirituality will eventually seriously interact, because as we start to go outside of the space-time headset and let go of the scientific physicalism, and if the idea that conscious agents outside of space-time catches on, then we really will be using science to start to explore what spiritual traditions have been talking about for thousands of years. But the spiritual traditions, they've said for thousands of years that space-time isn't fundamental. There's something beyond space-time. But they haven't had the tools, the mathematical tools or the empirical tools. So science both bring something to the table. The spiritual traditions have thousands of years outside of space-time. They have a lot of insights. Science has been inside space-time studying the headset and has sharpened all these tools of mathematical theories and careful experiments. Yeah, it's going to be great. When we bring the two together, we will probably be able to learn from the insights of the spiritual traditions and also find it, where there's nonsense, right? There's nonsense in science and there's nonsense in spiritual traditions. How do we find it out? Well, when we make our ideas precise enough to make them testable or to show that they're inconsistent or whatever. And I've enjoyed, I talk with spiritual teachers and so forth. Rupert Spira and I've had a couple of
Oh,
conversations.
really? I've actually met him in Oxford, yeah, when I was studying.
Yeah, and I've met him too in San Jose a couple times.
My father
Great
even went
breakfast.
to one of his retreats, actually, in Italy.
Yeah, no, he's brilliant, and we enjoy talking with each other. It's just really quite nice. I had a conversation with the Dalai Lama back in 2017 or something like that, 2018, um, in Pisa, Italy, about science and spirituality. I'm good friends with Deepak Chopra, and I've also talked with a Jewish rabbi, Joseph Dweck, and I've talked with Islamic spiritual people as well. So I'm quite open to talking with various spiritual traditions with the same attitude that I have towards science, which is hard-nosed. I'm hard-nosed about the science. We're out here to learn. And I'm also hard-nosed about the spirituality. We don't want to fool ourselves, and it's very easy to fool ourselves. What science brings to the table is a precision of language that, in the best case, tells you the limits of your theory. That's what you want, is a theory that tells you your theory stops there. That's where your theory falls apart. And every theory will fall apart. When we just have language, which most spiritual traditions have, it's hard to find out the limits of your theory. Even though these spiritual traditions will say these words are just pointers. The pointer is not the way, the map is not the territory. They'll say that, but the followers don't really follow that. We end up with religious wars. We end up with dogmatism, fighting each other, and precision is a help, because when your own theory tells you, when Einstein's theory tells you your theory stops at 10 to the minus 33 centimeters, what can you say? Yeah, my theory stops at 10 to the minus 33 centimeters. Case closed. My theory doesn't go any further than that. Can't be dogmatic about space-time anymore. My own theory of space-time tells me not to be dogmatic about it. And that's what we need in the spiritual traditions, is when our own precise spiritual theories tell us their precise limits, then there's no excuse to be dogmatic anymore. We know what the limit of that pointer is, exactly what the limit of that pointer is. Don't take the pointer any further than this, or you're off on bogus territory. So that's what I see happening with science and spirituality. And by the way, I'm not saying that scientists are less dogmatic than anybody else. Scientists are people. It's science as a scientific enterprise, as a social enterprise, where we pit theories against each other and demand precision and demand experimental. That social enterprise is anti-dogmatic. It counters the innate dogmatism that most of us harbor. Right?
Yes, very well said. Yeah.
So that's what I see going forward. And ultimately then, when we have these precise theories, then we can make spiritual progress in understanding better and better pointers, because I think we're limited by our teachers. How good can they teach? What kind of pointers can they give us to help us move along in the spiritual path? Well, if their pointers are 3,000 years old and they haven't really evolved, maybe we can do better than that. Maybe we can come up with pointers that evolve. Wouldn't it be nice to have spiritual traditions where we're reading what was discovered last week that sort of transcends everything that we've been doing for the last few centuries? And every week, you go to church and you're learning the new discoveries in spirituality, and new ways to go deeper. That would be incredible. Instead of saying this is 2,000 years old or 3,000 years old, it must be true. No, it's 2,000 years old, 3,000 years old. Why haven't we made any more progress?
I guess the difficulty in you explaining just how much work it takes to be able to even understand some of this language, I think, is part of the hurdle here. It's wonderfully precise and wonderfully difficult, therefore.
It is, and that's why ultimately I would see that the genuine spiritual leaders would be the group that could really understand this and then translate it into everyday language that everybody could use. Just like no one understands all the theoretical physics that goes into an iPhone, but someone translated it into an iPhone and you're happy to use the iPhone.
Yeah.
You're very happy to use it.
What about the everyday? I mean, I think the religious, kind of the spiritual potential of this worldview, if it holds as well as it has held so far, at least as a possible worldview. I don't want to say that we've now proven that, but certainly there is a sense in which room has been made within science for this worldview of yours. And the spiritual, religious, divine, cosmic implications, I think, are for everyone to explore themselves, but it's pretty clear what kind of things one might find. What about every day? I have heard you say that thinking about this has made you feel like a lot of the things that we are really attached to is kind of, well, why be attached? You know, why would you be so attached to your car or whatever if it's just part of the headset? It's not part of the fundamental reality. I see the argument, but I would say that I'm partially unconvinced, because let's take selfishness aside. So let's think about me seeing a person, homeless person, doesn't have a home, doesn't have a car, isn't able to go see their dying parent because they don't have a mode of transportation, and they sleep in the rain. Well, I might really want to create a world where this person has a shelter and a mode of transportation. And I would be really, really quite mad if I work for that and then somebody just steals it off from this poor person. And I don't know if at that moment I would really be touched by an argument. Oh, don't worry, the car was just part of the headset. It's not part of the fundamental reality. Yes, but this person cannot go see their dying parent or whatever, you know. Like, so, although I'm not saying there isn't something there, but I do you hear the concern I have? Is that it, in a way, I mean, the selfishness maybe is the problem more than attachment to objects, or maybe attachment in some ways of understanding is the problem. But yeah, where does this way of looking at reality then start making a difference? Because it seems that material things, as far as they are tools for genuinely valuable goals, it doesn't really take value away from them. So what changes?
Well, in this interpretation in which there is this just one fundamental consciousness, and you and I are just avatars, different avatars that one consciousness is wearing, then the religious dictum, love your neighbor as yourself, makes sense, because your neighbor is yourself. That is you in a different headset. And that really is what true love is to recognize the other as not someone that you have to try to figure out how you might love this, but to realize, no, that's me. That is me, just in a different avatar. That's it. And so is my cat. And so is a mouse. And so is everything. It's me. So love your neighbor as yourself, because your neighbor is yourself. And if we really understand, I mean, that's either true or false. If it's true, it's the most profound truth that there is. And I think it is likely true. And we know as well that everything that you collect, all the goodies you collect in this world, disappear. You get a house, you get a mansion, you get a car, you get a reputation, you get your PhD, and Where does it go? You walk away from all. You walk away from all of it. We know that there's nothing that you do here that you keep. None. Nothing. So those are the facts, that nothing. And I can't even tell you, who my great grandparents were. Don't know their names. You probably can't either.
Great grandparents. Yeah. Only one, actually. Yeah.
And there were 16 or 32 of them, or
Yeah.
and I can't name all of them. So when you ask what's the point and what is the meaning of life, well, it certainly isn't collecting stuff, because you walk away from all that stuff. But my guess is that the one consciousness puts on different headsets and explores its potential. That's the way the one learns about itself, is by trying on. And this is, we just happen to be one of the cheaper headsets that the one has tried on. I was complaining about, this is one of the cheaper ones, but it tries on countless other headsets. And this is a trivial one, and explores the potentials in these various different headsets. And that's how it knows itself. There's some spiritual traditions that say that the formless can only know itself in contrast to forms. So plunge yourself into a world of forms, and then immerse yourself in it, identify with the forms, and then when you finally wake up and realize you're not that form, that's when you really understand who you are as the formless. And that may be, if I had to guess what life is about, that's what I would say is, we're here, we get plunged in, we completely identify with our careers and our jobs and collecting all this stuff and doing all this stuff and being important and so forth. And then all of a sudden we begin to realize, well, wait a minute, I'm going to walk away from all this stuff. And no one's going to care about my career. No one's going to even, my great grandkids won't even remember my name. So what's really going on here? What is this about? Well, it's not about getting stuff. It's not about being famous. It's not about, none of that stuff matters. It literally doesn't matter. And yet we spend our entire lives, up to some of us, all of our lives, until we die. And some of us, most of our lives, until we start to go, wait a minute, that doesn't make sense.
And so is maybe the reason I wanted to give that example earlier is that I've kind of come to think that when people say don't get attached to material things, part of it is, of course, that any attachment is going to bring tears one day. I think love is such a beautiful form of attachment that I'm happy crying. Attachment to a watch is not maybe worth it, but like I guess, like, sometimes I feel the arguments to be a bit cheap, because I know that there are people who get bigger houses just because of status, but I also, none of my friends even has a guest room where they could host their parents. And I live in central London, and there's all sorts of inconveniences that can become genuine inconveniences if you have insomnia. And so my friends who are moving, I don't see any of them moving for status reasons. They move for genuine reasons that anybody who cares for them would want to succeed. And so maybe it's not the fact that we want stuff as such, because sometimes stuff is good, like a shelter is good for you if you're sleeping in the rain, but it's when we want stuff in a way that comes from a place of competition, conflict.
Right. Wanting to be special.
Yes, instead of the kind of place where, as I would want it for anyone, I want a shelter for myself too, but I don't want it so that others wouldn't have as big of a shelter as me. Or
Right. And this is again what the spiritual traditions talk about. They say that there's this fundamental illusion. You think of yourself as a small object in space-time. That's what I am. I'm this 150 pound, 200 pound, whatever it might be, little object in space-time. And I need to, I'm only going to be here for a few years, and I need to do whatever I can to try to complete myself and be special. And I need to compete with you. You're trying to be special and complete yourself. And that's the illusion. And the reason it's a problem is because it's an illusion. It's false. In fact, on the spiritual view, you are infinite intelligence. You are the author of everything that you're seeing. You're not some little 150 pound thing inside of space-time.
Yeah. It's not you contrasted to that other.
That's right. And there's no need to be special. when you realize that it's this whole thing is me looking at myself. When I look at a rock, I'm looking at myself through a headset. That's what I'm seeing. When I look at you, I'm seeing myself, and I'm seeing another avatar of myself looking at me back. And so from that point of view, then this is about plunging yourself into the headset and losing yourself in the headset, and then waking up and recognizing, no, I am the actual reality behind the entire headset. And that's what I am. And there's no need for me to be special or to compete with anybody else, because the other is me. Then I love my neighbor as myself because the other is myself. So it's really, so the issue is not about a moral thing so much as just waking up from an illusion. Thinking yourself as a small, insignificant thing that needs to get special somehow, and need to be more special than all these other people, and waking up and realizing, oh, wait, I am more special than I could be in my wildest egoic dreams. I'm far more so special that you just have to laugh about all the egoic dreams of being the richest person on earth, or the smartest person, or the next nine. All those, they're paltry compared to what you already are. And so but there's some deep humility in which the one infinite intelligence plunges itself down, loses itself, and then painfully wakes itself up. But that seems to be a necessary part of self understanding and self knowledge. That's how the infinite knows itself, is by putting on different headsets and losing itself in the headsets, and then waking up. That's again, this is not science.
Yeah.
This is me talking outside my expertise, but you asked the question. So I want to say, when I talk about projecting into decorated permutations in space-time, that's science, and that's this other stuff. Take it with a grain of salt.
I always finish by asking guests about how the research they do has impacted their view on our species, on humanity. And I guess you can kind of take that to any direction you want. Starting to think about vision in a radical way, all the way to being, holy moly, this actually might explain particle physics, whatever that exactly means. How was it shaped, the way you look at this bipedal ape?
Well, before I used to be naturally quite judgmental about people and about myself. And now I'm recognizing that judgmentalism is just an illusion again on my part. If really it is the case that there is the one consciousness that's just putting on all these different headsets, and I'm seeing it as a person that robbed me. I've been robbed and so forth. That you can see it's a very different attitude toward the human being. It's not me judging people about their moral character and so forth. It's me saying, I used to do that, and it's still my emotional reaction, by the way. That's my emotions are that way. But now I'm looking at those emotions. I guess that I can look at those knee-jerk reactions of judgmentalism and so forth, and recognize them as much as an illusion as my knee-jerk reaction that the moon really is there, when my belief that the moon is there when no one looks. That's how I feel about it, because I feel I'm lost in the headset a lot of the time. But when I awake again, when I'm aware, then I realize there's no more reason for me to be judgmental about people than there is for me to believe the moon is there when I don't look. They're both an illusion. What's really there is me trying on various headsets and looking at what I do. So put it this way. Suppose you're playing a virtual reality game, and you put on your headset and bodysuit and get in there. There's two ways you can play that game. One is, this is just a game, and I'm having fun. And so I'm having fun. So I'm gonna go rob a bank. I'm gonna go, or it's me in the game, and I don't know it's a game. I think it's the reality. Now all of a sudden it's very serious. very, very serious. I get upset about things, and I get judgmental about people and so forth.
But would you go rob a bank now?
Well, I on either view, I don't recommend robbing the bank. So I'm not arguing for amoral behavior. But on the other hand, ultimately, I think when we take off the headset, we're going to realize that no one was really hurt. It was just a headset, right? Is
there a tension then between the two ways you can take it, where one is a kind of a more jubilant but perhaps more amoral direction? At the end of the day, it's not that big of a deal. And then there is the other one, which you suggested earlier, which is that my neighbor is me, therefore why would I ever hurt them? Do you think that those are two alternative directions, and everybody can it's like a buffet table, you pick your favorites, or are they somehow weaved to each other? Is there less tension than I see between them?
Well, I would say that probably we're here to wake up. That's what we're here in. And so that's why I don't recommend amoral behavior, because perseverating in amoral behavior is perseverating in being asleep. And the point is to wake up to the fact that I'm here to love my neighbor as myself, because my neighbor is myself, to wake up to that whole thing, and to wake up to the joy of love, and to wake up to the fact that I don't need to be special. I don't need to be more special than anybody else. I am that other person, and I am the dog, and I am the cat, and so I'm saying that ultimately the point of it, the morality, is not because cars are so important, or that bank accounts are so important, or that houses are so important. What's important is waking up. So you can see it's not at all supporting amoral behavior, but it's actually being very forgiving, and ultimately recognizing that in this realm nothing is lost. Ultimately, my guess is we're going to all take off the headset and laugh.
We'll laugh in an atemporal time, whatever that means.
Well, actually, it turns out we can have dynamics. You might say dynamics without time. Yes, dynamics without an arrow of time, no increasing entropy. But when you project that dynamics, the projection that loses information will force an arrow of time. So the arrow of time that we experience in this headset is entirely an artifact of loss of information in the projection. The original dynamics has no increasing entropy. So that's how you can actually have a dynamics without an arrow of time.
So that underlying reality is not going from order to chaos.
No. It's already complete.
Professor Donald Hoffman, thank you so much for your research and your incredibly generous time today.
My pleasure. Thanks so much, Hilary.
So that was it for today. I hope that you enjoyed it. If you did, please do consider supporting my work. First, by subscribing to the podcast if you have not done so yet, and also by becoming a Patreon member at patreon.com/onhumans. Do also check out the OnHumans newsletter at onhumans.substack.com. Anyway, until next time, take care.